So usual question with the twist, because I don't just want the new name, I want you to find some old names. As we said in the movie, carboxylic acids, more than any other class of compounds, have tons and tons of old fun names. So find a few. So C6H12O2 is the first isomer. It's going to be the one based on a 6-carbon chain. Only one way to do that, with the acid group at the end of the chain, so hexanoic acid. Old name for that is caproic acid, named after the goat, as in Capricorn, because it smells like a wet goat. Smelled a wet dog before? Imagine how badly a wet goat would smell. Now let's move to 5 carbons. So obviously it's going to be based upon pentanoic acid, and then we have a methyl group spare. Well, that methyl group can go in the 2 position. Carbon 1, of course, determined by the acid without any ambiguity at all. So 2-methyl pentanoic acid, old name for pentanoic acid, valeric acid. Or we can put the methyl group in the 3-carbon position to give us 3-methyl pentanoic or 3-methyl valeric acid. Or we can put it in the 4 position to give us the 4-methyl pentanoic acid, the 4-methyl valeric acid. Or this is the one that the old-time chemists chose to call the isomer of caproic acid. So this is actually isocaproic acid. Always, of course, need to be on the lookout for stereogenic or chiral carbons. All of the ones here have got, of course, at least 2 hydrogens on, at least 2 hydrogens there, 2 hydrogens, 2 hydrogens, 2 hydrogens. This carbon's got 2 methyl groups. However, we have both in the 2-methyl at the 2 position and the 3-methyl at the 3 position chiral carbons. Here you've got the methyl, the acid group, a propyl group, and a hydrogen. So let's draw them out. First of all, let's stick the hydrogen at the back and draw it this one way. Really doesn't matter what way round you do it, as long as then the second enantiomer you draw as its mirror image. And the easiest way to do that is imagine a mirror plane here and reflect this molecule in it, so that what was on the left is now on the right, what was on the right is now on the left, what was up is still up, what was forward is still forward, and what was back is still back. Signing priority here. Obviously, carbon with 3 oxygens on it is better than a carbon with 2 hydrogens and a carbon, and that's better than a carbon with 3 hydrogens. So the acid group, priority 1, propyl, priority 2, methyl, priority 3. So this one here, we're going 1, 2, 3 clockwise, which makes that the R. And this one here, we're going 1, 2, 3 anti-clockwise, which makes that one the S. Same idea for the 3-methyl pentanoic acid. Carbon 3 has got a funny old bit with the acid group here, a methyl group, and then an ethyl group. So let's add in the missing hydrogen. Draw one with the hydrogen going back, mirror image of it. So what's up is up, what was left is now right, what was right is now left. And so we get that pretty little molecule. Again, let's assign priorities. Obviously hydrogen, worst priority, methyl, third priority. Now let's do it between the ethyl and this sort of ethyl acid bitty here. So starting off here, CH2, CH2, so no difference there. But now here you have a carbon with effectively 3 oxygens. Here is a carbon with 3 hydrogens. So again, this acid group is top priority. So for this enantiomer here, acid group number 1, ethyl number 2, methyl number 3. So clockwise, making that the R. And then here the acid group number 1, ethyl number 2, methyl number 3, we're going 1, 2, 3 anti-clockwise, which makes that one the S. So we've done the 6 carbons, we've done the 5 carbons. Let's move to the 4 carbon possibility. So things going to be based upon butanoic acid. So 1, 2, 3, fourth one is still going to be there. When we take out 4 carbons, there's 2 left. So we could have those as 2 methyl groups. So we could put both methyl groups on carbon 2 to give us 2,2-dimethyl butanoic acid. The old name for butanoic is, of course, butyric acid. We could put both the methyl groups on carbon 3, so 3,3-dimethyl butanoic acid or 3,3-dimethyl butyric acid. You can see another old name I think is kind of cute. This is a tert-butyl group stuck on the end of acetic acid there. So tert-butyl acetic acid, one of the old names for it. And then, of course, we can put, instead of 2 methyls, we can put on 1 ethyl group there. So we get 2 ethyl butanoic acid. That's the 1, 2, 3, 4 butanoic acid. There's the 2 ethyl coming out of it. Otherwise known as diethyl acetic acid, which is rather a cute one there. And then, of course, going back to the methyls, instead of both on 1 carbon, we could put 1 on carbon 2, 1 on carbon 3, giving us a 2,3-dimethyl butyric acid. So think about stereogenic ones. Well, 3 hydrogens, 2 hydrogens, 2 methyls, 3 hydrogens, 2 hydrogens, 2 methyls. This one here, this carbon's got 2 ethyl groups, 2 hydrogens, 3 hydrogens. But now here we've actually got a fun one, because this carbon's got 2 methyl groups on it, but this carbon, carbon 2, has a methyl group, the acid group, effectively an isopropyl group, and then of course a hydrogen. So again, we can draw the 2 enantiomers for this. Start off, hydrogen at the back right there. So when we come to it, COOH is number 1, isopropyl is number 2, methyl number 3. Let's just make sure we see that the acid group is better than the isopropyl group. Here you've got a carbon with 3 oxygens. Here you've got a carbon with 2 carbons. So 1, 2, 3. So this would be, when we get to it, the R. Let's draw the mirror image of it. Again, what was up's up, what was back is back, what was forward is forward, what was left is right, what was right is left. So this is the R, as we've said, and now this one here, acid group number 1, isopropyl number 2, methyl number 3, going 1, 2, 3, making that the S. So there you go, 11 different isomers.